Okay, today we're going to talk about the significance of a formula and binary ionic compounds. So, our objectives are to be able to tell important parts of a chemical formula, to know what parentheses mean, to know subscripts, okay, and finally, to be able to write some formulas if we are given the name of the compound. So we're going to start our discussion of nomenclature. Now, people, it's very important that you understand nomenclature, because if you can't take the name of a chemical and write the formula for the chemical, you are going to struggle in chemistry class until about the end of the third 9 weeks, because we are doing it a ton. So it is imperative that you understand what is going on when we are naming and writing formulas of names. Okay? So, the significance of a chemical formula. Okay, like I said, our objectives. After we do these review notes, you should be able to state the significance of a formula. You should be able to name some monoatomic ions. I told you to take out your ion sheets. We'll be using those coming up here. And finally, to write the formula for binary ionic compounds. Right here, glucose. Here's the chemical formula for glucose. What does this tell us? What does this formula tell us? Anybody got any ideas? No? I know you watched the video. What's something that this tells you, Colin? You don't know? Well, you watched the video last night, didn't you? Yeah, I forget. Well, what's that? There are 6 carbons. What else? There are 12 hydrogen. There are 6 oxygen. All right? So this tells us the number of each element that is involved there. Now, let's look at this one. I've got parentheses around my phosphate. That is a polyatomic ion. When I'm dealing with polyatomic ions, if I have more than one, I need to put parentheses. So this is telling me that I have 2 of the polyatomic ion phosphate. So if I'm looking at each one individually, I have 3 calciums, I have 2 phosphates, and I have 8 oxygens. Okay? So those parentheses tell me that I am doubling. If there's nothing behind, if there's no subscript behind an element, that means it is 1. Now look at this one. Okay? This one here has a polyatomic ion, sulfate. But notice there's nothing past this. This is incorrectly written, because if I don't have more than 1, I do not need parentheses. So those parentheses are incorrect. If it were me and you did this on a quiz, I would probably just scribble out the parentheses and say, hey, you don't need those. If it's WebAssign, they will count you wrong. They will count it wrong. So do not use parentheses if we don't need them. Now, a monoatomic ion. Let's go ahead and break these down. Mono, 1 atom. So these are ions that consist of 1 atom. I want you to take out the ion sheet that has a list that says at the top, a list of common ions, and on the back it has a mini periodic table. So I want you to look at that one because the whole left-hand side of that is dealing with monoatomic ions. Now, we covered bonding before we came to nomenclature because we need to know what's going on with bonding to help us name things. We said that there were different types of bonding, ionic bonding and covalent bonding. Well, when we're talking about monoatomic ions, we are talking about ionic bonding. Now, let's look at sodium. You did the electron dot notation for sodium earlier on the year, and if you find sodium on your periodic table, you know that sodium's a group 1 element. It's an alkali metal. So, sodium has one valence electron on its outermost energy level. The first energy level is filled. The second energy level is filled. The third energy level has one electron. So if I were going to draw the electron dot notation for sodium, it would look like this, where I would have one electron around the sodium. Now, in order for sodium to achieve its stability, it wants to lose that one electron so that it has a full outermost energy level. So what sodium does is it gets rid of that electron. Now, instead of having 11 protons and 11 electrons, sodium has 11 protons. It only has 10 electrons. So the net charge of sodium is a +1. When I do that, I have now created the sodium ion, Na+1. So that would be a cation. A cation because it is a positive ion. Let's look at chlorine. If I look at chlorine on my periodic table, it's in group 17. Chlorine is a halogen. Chlorine would have 7 valence electrons. So if I were going to draw the electron dot notation for chlorine, it would look like this. Now, with my electron dot notation with chlorine, it is 1 electron away from filling its outermost shell. So what chlorine would like to do is it would like to gain an electron. So when it does so, it has gained that electron right there. Now, instead of having 17 protons and 17 electrons, chlorine now has 17 protons and 18 electrons. So it has one more electron, therefore, chlorine has a -1 charge. So as a monoatomic anion, if it is a negative ion, it's called an anion. As a monoatomic anion, chlorine has a -1 charge. Now, when we name this, when we're talking about monoatomic anions, when we're talking about ions with a negative charge, we get rid of this INE and we end it with an IDE. So if you look at the monoatomic anions on that list, you'll see hydride, fluoride, chloride, bromide. So this particular anion would be the chloride anion. So anytime I see the chloride, I know that it's Cl-1. Now, what does this all mean? Well, when we talked about bonding, okay, we said that, hey, sodium and chlorine, they are a good match. Why is sodium and chlorine a good match? Well, sodium wants to dump that electron, and chlorine wants to gain one. So when we have this ionic bonding occurring, sodium gives its electron to chlorine. Sodium's a plus charge, chlorine is a minus charge. Okay, what is the net charge when I combine those two? Plus 1 minus 1 equals 0. So whenever we have an ionic compound, we have to have a net charge of 0. So what I have there formed is sodium chloride. Now let's look at calcium. Calcium is an alkaline earth metal. Calcium is in group 2. Calcium would have an electron dot notation right here of 2 dots. Now, if calcium were to pair up with chlorine, I would need to have one chlorine. I would need to have another chlorine. Because watch, if I get rid of that electron, I still need one more chlorine to get rid of the other electron, correct? So when I do so, I now have a 2 plus for calcium, and I have 2 different 1 minuses. So if I were going to write the ionic compound, if I were going to write the ionic formula for this particular compound, I would write, and I don't know why I'm not writing, because I don't have a green light here. Green light me. All right. I would write I guess I'm not going to write it there. I'll write it on the board. I would write CaCl with a subscript 2. Okay? CaCl2. Because I needed 2 chlorines to go with my calcium. Now, what was my net charge? Still a net 0, right? That's an ionic formula. Now, let's talk about aluminum oxide. Now, we're going to name aluminum oxide. So, as I am naming this, I need to find my charges for my individual ions. So, when I have aluminum, find aluminum on that ion sheet. What is aluminum on your ion sheet? All right, so we said that aluminum was, we just said aluminum was a 3 plus, right? What is oxygen? What is the oxide ion? O2 negative. Now, when we discussed, when you watched the video, there were different ways we can do this. Well, one way that I taught you was the crisscross, meaning you could take and crisscross, so I would have Al2, because I'd bring my 2 down, O3. So that is one way in which I could write the formula for that. Now, another way that I like to do this, okay, let me get back to my original here. Another way that I do it is I think of least common multiples. So if I have Al3 plus and I have O2 minus, I can see that my least common multiple is 6. Okay, so in order to get to 6, I would need to have 2 aluminums and I would need to have 3 oxygens to get to 6. Now, yet another way that we teach this, okay, yet another way that we teach this. And we do this a lot more when we're dealing with physical science. So if you took physical science, you've probably seen this before, is I can see my charges are off balance. Okay? I've got not enough negatives. I got too much positives. So when I add a second one of these, now they're still off balance. So I need to add a second one of these and then a third one of these. So when I get to the bottom line, I have added 2 aluminums and 3 oxygens to get my net charge equal to 0. So whichever way you want to do it, it does not matter to me. Okay, whichever way you see things. Like I said, I like to look at them, and I like to see least common multiples. I will tell you this, though. You're going to see one coming up here that is dealing with, if you crisscross it, it will be wrong. Okay, if you crisscross it, it will be wrong. So that the crisscross method is not always going to give you a correct answer. Now let's look at barium bromide. Okay, what is the barium ion? Find it on your monoatomic ion list. What is barium? Barium is Ba 2+. What is bromide? Okay, it is Br, let's include Br 1 negative. So, I've got my 2 ions, right? I can see that my charges are not equal to 0, so I need to have Ba, but I need to have 2 bromines. I need to have 2 bromines because I've got 2 minus, I only have a 1 plus. Make sense? Now, this one brings a new part into play because I have this thing right here. That is a Roman numeral. I want you to look at your periodic table. On your periodic table, I want you to find the oxidation state. Okay? So look at lead, and lead is element number 82. So look at lead and find the oxidation state of lead. What do you see? You see a +2 and a +4. Okay, is one of them darker than the other one? Which one's darker? +2? What does that mean if it's darker? It's more stable? Okay. So, I'm looking at that, and by having the oxidation numbers, if there are more than one, you need to have a Roman numeral telling you which one. This Roman numeral up here, IV, is the Roman numeral for 4. Okay? Are you folks familiar with Roman numerals? Okay? I don't know why, but when I was a kid, my mom and dad had a clock that didn't have any numbers like our clock up here. It had all Roman numerals. So if I wanted to read the clock when I was a kid, I had to know what Roman numerals were. So that helped me out. But this is Roman numeral number 4. Okay? Look at, let's say, calcium. How many oxidation states does calcium have? Just has one, it's a 2, right? So, we wouldn't need a Roman numeral for calcium. If you would put a Roman numeral and you don't need one, it's not correct. Okay? Look at copper, element number 29. How many oxidation states does copper have? 2. So I would need a Roman numeral. Copper could be a 1+ or a 2+. Look at zinc, element number 30, right beside it. How many oxidation numbers does zinc have? It only has one, so I don't need a Roman numeral. Look at manganese, element number 25. Manganese up here has a 2, a 3, a 4, a 6, and a 7. Okay? So manganese could take all of those oxidation states. So manganese could be a 2, a +2, +3, +4, what else did I say? +6 and +7. It could be all of those. We have to tell which one. So as I'm looking at this, lead, Roman numeral 4, oxide. What does that tell me? Well, it tells me that I'm dealing with lead 4+, because the Roman numeral 4 signifies that I have a 4+ charge. What is my anion for oxygen or oxide? 2-. Okay? This is the one that I told you if you crisscross it, you get it wrong. Okay? If you crisscross it, you get it wrong. Because the correct formula for lead 4 oxide is PbO2. PbO2 is the correct answer. If you would crisscross that, you would get Pb2O4, which would not be correct. Moving on. Hydrogen peroxide. This is a great one, folks, because of a couple of things. First of all, what is hydrogen? Now, if you look on your ion sheets, hydrogen can be a +1, hydrogen can be a -1. Okay, so it could be hydrogen ion, it could be the hydride ion. Now, how can I tell whether it's a plus or a minus? Well, I rarely see hydrogen as a negative ion. I've seen it before, but very rarely. The majority of the time, it is the positive. But when it is a negative, I usually see it with an alkali metal, something like lithium hydride. Which brings me to another point that I don't think I've talked about yet. The positive one always is first. The negative one always is second. Okay? Now, my other class is way ahead of you because they're in double periods right now, but I still, even though we've done this about a month ago maybe, I still saw today someone wrote iron 2 chloride like that, which is not correct because the positive one always comes first. So this is wrong. The positive ion comes first, the negative one comes second. So, like I was telling you before, usually when I am going to see, I think the most common one that I saw where I had hydrogen being a negative charge was lithium hydride right there. The majority of time, hydrogen is a plus charge. So, I see hydrogen here. Okay. What is peroxide? Is peroxide on your ion sheet? Can you find it? O2, 2 negative. So, as I'm looking at this, when I write out hydrogen peroxide, it is H2O2. Now, you don't reduce that down. It's still H2O2. Okay? Don't reduce it down. You just have to notice when I see something like that, it's a peroxide. Now, the most common times that you're going to see a peroxide, they're going to be alkali metals with the peroxide. So I'll see an Li2O2. I've seen an Na2O2. Those and hydrogen are the most common peroxides that I see. So if you see that alkali metal with the O2 where you think, hey, I probably should reduce that. Well, wait a second. Is that a peroxide? Because if it is a peroxide, we cannot reduce that. Now, this very last one here, I'm going to give you a second, and I want you to go ahead and write the formula for this one. You try it yourself to see how you do. Now, calcium. I know that calcium is a Ca2+. Phosphide is a P3-. So if I am going to write the chemical formula, I'm going to write Ca3P2 to get my net charges equal to 0. So, ladies and gentlemen, calcium phosphide. Final answer.